Gonna record. My microphone is plugged in properly this time, so that's always helpful. Hi, folks. Hi, no hi Zoomers. Hi, YouTubers. Hi, Roomers. Yes, and see, now Vladimir has some friends to sit over on the other side of the class with, so that's good. So thanks for being here, folks. Yeah, we're trying to figure out what's going on. Let's see. We are here. Yeah, November. My goodness. So yes, formative assessment number 4. Give it your best shot. You get your 3 points no matter what. Okay, I'm just going to enter them. So you will see your actual feedback on Tuesday morning, and we'll be able to go through that. I'm planning on posting a video that finishes out lecture 4, the estimation parts that I recorded last time, and actually recorded it in my basement last time, so it would be the same thing in terms of what you would experience. Next week, we'll see if we started on Tuesday, but Thursday for sure, we're starting a little bit different topic. So we've covered pretty much all what I would say like the basic foundational aspects of multi-level modeling with cluster data are. Now we add things. So the next unit is about cross-classified designs where there's more than one kind of nesting. So a few of you have these in your projects. I know Dan, hi, if you're listening, her baby is sick, she wanted to be here. She has item responses from different respondents, and so her model is going to have item responses nested in persons, but also item responses are nested in items. Because in the same way that some people are higher or lower than each other, some items are more or less difficult. It's the same concept. And so then in phrasing the model that way, rather than having item-specific parameters, so like in factor analysis or IRT, you would have each item would get its own difficulty or its own factor loading or its own intercept or its own whatever. Rather than do those as fixed effects, it's a random effect. So a separate random intercept for item difficulty differences. And because it's an additive model, it's easiness instead of difficulty. But then you can predict with features of the items why some items are more difficult. And not within multi-level modeling software, but in life, you can also predict why loadings are stronger in some items than others. So you can put a linear model on the measurement parameters, essentially, which is very cool extension. So that's one use case I wanted to talk about, subjects cross with items. Another one that comes into play is cross-classified designs. So I have some fake data from the Hawks book. I'm quite certain it's fake because there's exactly 1,000 people and all the cells are balanced. We have kids that are nested in primary schools and kids that are also nested in secondary schools, but not everybody who went to the same primary goes to the same secondary and vice versa. So you can control for clustering that happened previously, because if you think about like your primary school experiences might have some impact on your outcomes now because you have this shared history, and you can control for your current clustering as it relates to the outcome. So multiple kinds of level 2 units. That's what this entails. And potentially a more complex design. So I'm going to say your name wrong. Is it E or I? A. 3 strikes and I'm out. Do you want to tell them about your project design? Because you've got some crossing and nesting in yours too. It's crossed. So a 3-level hierarchical with a crossing at the top, right?
Trying to make a pie shape.
Yeah, so we'll look forward to that presentation. Like, seriously, like if you get the empty model right, like you win at that point. Like, that's the expectations. So that's one kind of extension. There's also something called multiple membership models, which is usually taught at the same time. I have some resources that Don Hedeker made that I'm going to link to. He does a really good job explaining this stuff. But for example, if you went to high school A your freshman year and then your family moved and you went to high school B your next year, like you need to be in both with respect to the nesting. So there are various ways to do that. You can either split your random intercept essentially, like the proportion of time that you were in each school is what would go into the model, or you could have ones across the board. These are sometimes phrased as nested models, but even if they're non-nested, you can compare them with if you're using maximum likelihood at least. So there's all kinds of cool stuff, yeah.
So is that what I would have had to know if I could identify easily who was in like this this class and then they repeated the class.
Mm-hmm. Yeah, I think because what you would you'd need to decide as the researcher or investigator, do you think that the effect of the class is acute, like temporary and it goes away, or does it stay with you? Because you would set up sort of like a layered random intercept where you've been stays with you and you pick up where you are now each time versus something that turns on and turns off. So as an example, if you are measuring an outcome that is something like teachers' ratings of aggressive behavior, let's just say, there's going to be some clustering there because the teacher is the one providing the ratings of the students. So teachers are going to have different opinions as to what aggressive is, right? Different standards. Some are stricter than others. So in that sense, I would not expect that who your teacher was last year to matter. Because it's like a teacher opinion thing, and it's like once you're out of the classroom, you're out. Right. But if you're measuring some sort of academic achievement type outcome, who you had last year could very well relate to how well you're doing this year. So then like the effect of having a good teacher or a bad teacher can stay with you to some extent. So there's ways of phrasing models to look at those kinds of extra layers of dependency, shall I say, in complex sampling designs. So just a little bit of that so that you've seen it before and some resources in case you have to deal with that. And then it's your turn, folks.
What?
Yeah, one more unit and then it's your turn. So I have a day planned I had check-in discussion. We'll see if I want to do that or if lecture 5 and the examples bleed over into that day. We'll see. I just wanted to leave something open. But yeah, then we have no class the Thursday before Thanksgiving. I decided everyone's usually gone or checked out mentally by then, so we're just going to be done. Except Vladimir, he gets to defend his comps that day. So it actually worked out very well that I had canceled class because that's the one Thursday afternoon that I'm not busy. Then we have Thanksgiving break or fall break as it is called here, and nothing is happening, and then nothing is due, and then we start presentations. So yeah, we're like almost there.
Wow.
It's crazy. I feel like it's still August in my head somehow, even though I'm in a sweater and wearing an actual coat to work today. So that's what's coming up. Stuff from last year, just to remind folks, and I've pointed this out to those of you for whom it's relevant, but I always keep the last version of the class active too. It just has a different link. Things that we got to last time that we're not getting to this time, so that I could make room for the presentations, was generalized models. So lecture 6 and example 6A is for categorical outcomes. 6B is for counts, if I remember correctly, yep. Then we also had a unit on generalized models that are crossed as well, because that is explanatory item response theory. So I snuck in that into the clustered class last time because there wasn't a good place for it. And then we got into multivariate multi-level models using multi-level structural equation modeling and 3-level models. And so I've got a lot of resources and examples for those things. I didn't get a chance to spend a whole lot of time. As you can see, everything's shoved into the last 3 squares. But there are other examples of things that you may find useful. And if at now or in the future, you're do you have an example that looks like this? Just email me and I can probably tell you oh, I did that 5 years ago. I have one of those. You'd be surprised. All right. Those were the things I had wanted to say. Am I forgetting anything? Any questions? We're good. Are we ready to finish example 4? They're no, did we start example 4? Example 4 is real data. Unlike some of my other examples that I'm pretty sure are fake or were messed with, example 4 is real data from a Midwestern rectangular state. We are predicting end of 10th grade math achievement outcomes of students who are nested in schools. You can see the sample size there is quite large at level 1, 139 schools, and there's one predictor: whether a student pays for their lunch, gets a reduced price lunch, or a free lunch. That's it. 23 pages, one predictor. All right, do you want to kind of go through the beginning parts of this? Because we got about halfway through, I think, but it was a while ago. It feels like that psychologically at least. What do we think? Review? Re-go over? Review. All right, cool. So Data processing steps, rather than, I should say, in addition to creating coding for your predictors. So this is the coding scheme that I'm going to be using, illustrated in this box here. It's called sequential coding. There's probably other names for it too, but essentially the benefit of this coding scheme is that I can first differentiate the difference between students who pay for their lunch, that's what P stands for, versus get some kind of discount. So grouping the reduced and free together. So RF, that's what that means. Then I can further delineate if there's any differences between the types of discounts, the reduced versus free. Like, is it just being poor or is it being like more poor? Like, where is the distinction? So this is an empirical question. So where we had been up to this point is just this one, the binary predictor. This is a level 1 variable, which means that I need to account for the potential of contextual effects. Given that I did not have any other data set to pull from, I computed the proportion of students who get a discount within each school, and I'm using that as an observed level 2 variable. If I had like district level data where they could say like for this school, these are the rates of free and reduced lunch, like that would be a better variable, but this is what I got. So in terms of descriptive statistics, I had that here at both levels of the model. So we're going to have, let me see here, highlight, there we go. Cluster mean math, cluster mean of the first binary predictor about discounted lunch, and then the cluster mean of the second one as well. So it looks like on the whole, about 30% of the students get some kind of discount, and 20% get free lunch, so about 10% get reduced essentially. And these are, like each of these is just an indicator variable, so I could make sure that my coding was working correctly. So these are the proportions in this little box here that represent like our reference school in terms of composition. So I'm centering my new cluster mean predictors such that 70% of the students would get paid lunch, 11% get reduced, and then 19% get free. So that's what these comments here are meant to indicate in terms of, that's why I picked those numbers. I picked the ones that are the mean. That's a reasonable thing to do. So we have a correlation at level 2 of almost 0.8, negative 0.8, between school mean math and the proportion of kids who get discounted lunch. So it's a huge effect. I don't want to spoil the surprise, but I'll just tell you, we end up with a pseudo R-square for the school level intercept variance of 0.7. 70% of the variance in school mean math scores has to do with poverty. It's really shocking. That's the punchline to the whole thing there. So contextual effects are a big deal in this case. I also wanted to remind folks that when you are reporting correlations in multi-level data, they need to be multi-level also. So the first correlation between student level math and student level discounted lunch is negative 0.36. If I cluster mean center each of those, it drops to negative 0.23. And if I add the level 2 means to this level 1 data set, I get a different correlation because of different weighting, but you can see it's still strongly negative. So this correlation is smushed. That's the punchline here. I did not include in this table the second binary variable because it doesn't mean what we think it does in isolation. So this is something that I run into in practice, and I haven't really come up with a good strategy for dealing with it. Let me put it this way. Go back to the coding scheme. This variable is unambiguous as to what it means. It is the difference between paying for lunch and getting some kind of discount. Okay. Once these two are both in the model at the same time, this second one differentiates these two sets of ones. And it pulls apart the free from the reduced. But if this is not in the model, it doesn't do that. Like if I put that column in all by itself, I am lumping together the paid and the reduced versus the free. So that's not the intent of the variable. So I could put that in the correlation matrix, but to me that variable doesn't mean anything. Like you wouldn't do that in practice. You wouldn't put together the paid and reduced and compare them to free. You could, but it doesn't mean it doesn't mean what I want it to mean. Let's put it that way. So I didn't put that in the correlation matrix. Okay, intra-class correlations. Yeah, question? Can we do proportions of? Get a discount, yeah. That would be the same thing in reverse, wouldn't it? Like paid is its own group versus the other two. That's what I have. What the other variable, what it is going to mean in the model is the difference between reduced and free specifically. What it means in the correlation table is paid and reduced together versus free. Not helping. Okay, ask your question again, please.
What I was thinking is, this is, the correlation is not, so for the correlation, we can look at each variable separately because we are not taking them. So it will indicate if the student is paying for this, what is the proportion of students paying in that school as its own, rather than just comparing it with another group and say what is the proportion that is getting free lunch and what is the proportion that is getting to school.
So yeah, I think you're talking about these variables. So I did make 3 indicators as to like you're in that group. You could use these and interpret correlations to the extent that you're comfortable lumping together the different kinds of zeros. So if you wanted to make an argument, right, that you just need to know like this first one is essentially what I have. It's paid versus discount. But like this one would be just for the people who have reduced, and it would lump together the paid and the free, which I would think is weird. So I think it's like you can examine correlations if it is a meaningful variable that you've created with respect to the zeros and the ones. I think. Maybe it's a compromise. I think we're talking about the same thing, maybe.
I think you are talking about the comparison with the reference group. But in my case, I'm talking about the interest is just the people. So what is the proportion of paid people in your school? How does that relate to mathematics, for example?
Mm-hmm.
Then what is the proportion of free in your school, regardless of what the other population is correlating with the outcome of the test? And what is the proportion of those who get reduced? How does that impact the outcomes activities?
Yes, yes. So we're talking about computing the school proportion of each of these binary variables and potentially correlating that with like cluster mean math or the school level math outcome. Yes, yeah. I think you can do that to the extent that you're comfortable with the zeros and ones.
Yeah, based on that, now I'm interested in the difference between the marginal relationship between the categories and the outcome and the conditional relationship. For instance, we could use the original variable, the indicators, in a multi-level model with only that variable, let's say 2 categories, right? One would be the implicit. I'm thinking that we could have some kind of effect sizes for those specific categories, and we could see what the relationship between that specific category controlling for the others and the outcome is. Because just using correlations, we would be looking at the bivariate relationship between the specific category and the outcome, but in the model, we would be looking at the control relationship. I don't know if that makes sense.
Mm-hmm.
There is a difference to me between what could the correlation would say and what a model would say. And we could use effect sizes and correlations to explore that relationship. But I think the model is a more robust way to explore those kind of relationships.
Okay, so let me make sure that's captured for the recording. The suggestion was, there's a bivariate correlation versus a conditional or a unique relationship that's in a model. Is there a way to make them comparable? Is that the question?
I think think that both are different.
They are different,
And
yes.
both could help to understand what the relationship between that specific predictor and the outcome is.
So there is a way within a correlation framework you can compute partial correlations or semi-partial correlations that control for things in whatever pattern that you want, so long as you can control via linear relationships only. That's the trick.
Yeah, that's part of it.
Yeah, because like in a model, you can build in piecewise slopes or quadratic slopes or like any kind of thing that you can't build into a correlation matrix. Because if you correlate a variable with x squared, you're not correlating it with a quadratic anything because x squared is both linear and quadratic. So like you can't pull it apart as readily. So I see models as much more flexible, but you're right in that unique effects and bivariate effects are not the same thing. You could fit separate models to get a bivariate analog. Yeah.
Just one quick follow-up question, Lisa. Now that we're talking about it, which is interesting, it is the same. Sorry, but to me, one thing would be the correlation between the original predictor and the outcome. Let's say we have a categorical predictor with 3 categories.
Mm-hmm.
So that would be, what that would be, some kind of Pearson correlation between a categorical variable and one continuous outcome?
If it's nominal or ordinal, no, I wouldn't put a Pearson correlation on it.
Yeah.
Point by serial? Is that if it's ordinal? Is that the
I'm
one?
not sure, but I think you're right. So my question is, that's one thing, but when you create these binary indicators, that would be, I think, a biserial correlation.
Yeah, that's the one.
So if that's the case, could we compare the results of a correlation using the original predictor and the outcome and the other correlations using the category-specific indicators with respect to the outcome? Should all of these different correlations lead to the same conclusion about
I don't think
these
so.
things?
So once you cross out of like Pearson land, where it's based on means, variances, and covariances, and you head over into like pretend underlying distribution variable lands, like the polyquarks, the tetraquarks, the biserials, the polyserials, all that stuff, like you're not going to get the same answer because but it's based on different information, I think.
Yes, that makes sense, yeah.
So you could compute things multiple ways and let your reader decide which one they like, potentially.
Hey, publisher, which way do you want me to do it?
Well, so you could pick a lane for the paper, but then add a supplement that presents additional results.
appendix.
Yeah, yeah, because I mean, journals nowadays a lot of journals are completely online, like they don't even make physical copies anymore. But certainly, supplemental appendices aren't subject to any kind of like formatting or page limits. So you can include whatever you'd like. So that may be, if there's multiple possibilities for something, that would be probably a reasonable approach.
Well, thanks.
So, yeah, thanks for the discussion. Okay, empty models. Intraclass correlation for math is 0.15. Okay, so hang on to that number because we will need to keep that as contextual for adding predictors that explain variance. So I told you the punchline to my story, right? 70% of the school level variance is due to poverty. It's 70% of the 15%.
So it's like 10% or 10.5%.
Yeah, so you got to multiply the two. Of means multiply. Remember that from like 7th grade math to get the actual like something resembling a total R squared for overall variance explained. So 70% of the 15%. I think we end up with 5% of the student variance, something like that. It's a lot smaller. So, massive design effect created by the fact that we have, let's see, 139 students on average per school and a large interclass correlation. For the same reasons, we have excellent reliability of the school means. Let's see. Lunch as an ordinal variable, so this is an example of how you would fit a generalized model. MEO-logit in Stata is what I'm using, and the CLMM function within the ordinal package in R to do this. So you don't have to do much that's different, other than keep in mind that this is in the model scale, which is logits, not the original variables. And if you're like, what does that mean? It's fine. Don't worry about it. You can still use this as the same sort of information, like 35% of this lunch variable is at the school level, That is justification for why we need to worry about contextual effects. So, all right, so that's what we did. First, how many fixed slopes are in this model in front of me?
Fixed.
How many fixed slopes? You got one vote for 0. Well, I have a predictor.
Oh, sorry.
There's got to be at least one.
I changed my vote.
You change your vote to 1? Okay, where is it? We're reviewing
Well,
notation.
It's beta 1 sub c, but that is only equal to gamma 1 sub 0, and gamma 1 sub 0 does not have a random slope, therefore it is fixed.
Yep, this thing right here.
If there was a u1c, then it would be a random slope, yes?
That's right. Yep, we're starting with fixed only for the time being. This is the first binary predictor where paid is 0 and reduced or free lunch is 1. Is this model good or not so good? Not even going to look at the numbers yet. Not so good. What's wrong, man? Yeah, I don't have some version of this predictor in level 2. So even though we just learned that 35% of this variable is actually school level information, we're assuming that it has the same relationship to math at the student level as at the school level. The within and between slopes are the same. Specifically, relative to kids who pay for lunch, kids who get a discount score about 9 points lower in math. However, this is not the student level effect, it's not the school level effect, it's the smushed effect. It's a weighted combination of the two, much more heavily weighted towards level 1 because that's where all the data are. In terms of explained variance, which one of these two variances should have been explained by this predictor? School level 2 or student level 1? Which one should have been explained by student lunch status? Well, I say should in the sense that the intent of adding a level 1 predictor is targeting, but you're right that that's where we're going. It should be level 1, right? I put in a student predictor to explain student variance in the outcome. I put in a school predictor to explain school variance in the outcome. You just swap out the noun and that sentence can keep being repeated, right? I put in item predictors to explain item variance in the outcome. I put in occasion predictors to explain occasion-specific variance in the outcome. It's the same idea. So the residual should have been reduced, and indeed it was, but the random intercept variance also got reduced. So that's a dead giveaway that you have a conflated effect, is if you only see one level 1 predictor in the model, not at level 2, but level 2 variance goes down anyway. So we got 40% of the intercept variance was explained by student level free and reduced lunch. So it is actually the composition effect that's doing that, not the student effect. Students explained 5%. So we fixed it. I'm adding in cluster mean of this variable. I am centering it at 0.3 to create a reference school that looks like the average. So keep in mind that the scale of this variable is 0 to 1. It is a proportion. That means a 1 unit change is talking about the difference between a hypothetical school with no poor kids and all poor kids, 0 to 1. So the slopes for this is going to be huge because the unit is the entire range of the variable. So just as a heads up. And I have a note over here. I think this was one of the review topics folks asked about. This version of the model, because it is the original level 1 predictor going in, I refer to this as a within contextual parameterization because that's what you get back. If you are interested in the between effect, which is the contribution of the school without controlling for the student version, you can add the two together. Within plus contextual is between. What if I wanted the between directly in the model? Is there a way I could set it up to get that instead? What could I do instead that would render level 2 between instead of contextual? Exactly, cluster mean center. We would subtract this variable right here from here, and then that means that there's only within variance here, there's only between variance here, and it would change to within between as opposed to within contextual. In the fixed effects, they are isomorphic. You can get back and forth with no problem. Not true in the random effects, though. So here's what we have. This right here is the contextual effect. So after controlling for whether you get a discounted lunch, and this is where to talk about this in units that are more interpretable, I move the decimal over one spot. So now what I would say is for every 10% more poor kids in your school's math is predicted to be lower by 1.7. So this is the idea of like, if you take your child and all their characteristics and you go dump them in another school, how is their score going to change based on the school's incremental contribution? Okay, that's contextual. Said differently, let me put this back here. This is the test as to whether smushing is okay. Because if within and between are the same, the contextual effect for their difference would be 0. Does 16 look like 0 to you? Not too much. Like 16 is pretty big, but you got to look at the standard error to be like, oh yeah, that is really big. I'll channel my intermediate self. This slope is 8 standard errors away from the null hypothesis of 0. That's a big effect. Outside the goalposts.
Exceeds 6 sigma,
Yeah.
which is
And a p-value that is significant to many, many decimal places. So yes, decidedly there is a contextual effect that we would want to pay attention to. What if reviewer 2 wants the between effect instead? Close. Add or subtract, it's one of the two, right? Which way does it go?
let's just do both.
The correct answer is add them up. Within plus contextual equals between. So I have a little function that adds Cohen's d and partial r effect sizes to each of these things. So this would be like a table that would be for reporting purposes. Estimate standard error at a minimum. Either p-values or stars, some way of indicating that. You don't need t, because t is just these two things, estimate over standard error. And you can pick whichever effect size makes more sense. I just wrote a function that gives them all, so you can have that for future reference. And then this is the result of that addition. -9 plus -16 is -26. So that's the full school effect. In terms of changing in the variances, at level 2, we picked up another 30%. At level 1, basically no change, just a little bit of wiggle there. This is as it should be. Because cluster mean lunch is a school characteristic, it should explain school variance. So level 1 should not change. Level 2 should decrease. And that's what happened. So the variance should decrease, indicating an R-square. So altogether, yeah, there's 69% of all the reasons why schools differ in math has to do with composition of free lunch. All right, how are we doing so far? Any that you want to hear again or ask about? All right, let me go back up to the equation here. How many fixed slopes are in this model? Same question as before. How many fixed slopes? He's voting for 1. You're voting for 2.
Oh wait, this is.
And this,
different
yeah,
model.
this is after
different
adding this one.
model.
Mhm.
Alrighty.
Yeah, I got 1 here. That's the one we had before, and I got 1 here. It's all good. So this model says that the discrepancy, it is 2 indeed, the discrepancy due to poverty. Can I say, I need to say that in a, like, The poor kid effect, can I say that? I'm trying to go for something that's shorter. This says the poor kid effect is fixed. Like the same for all schools, the same no matter what. You think that's the case? Do you think it sucks more to be poor in some schools than others? Mm-hmm. How do I operationalize the idea of sucks more to be poor in some schools than others? That's a random slope. Each school gets its own effect of sucking. Maybe don't put sucking in your manuscripts or your conference presentation, but, you know, I can do it here. Now, where does it go if we add a random slope? Where does it go with respect to the equation first and then the code? Yep, it will go right here. That's where we'll go. So let's make it happen. However, now I remember why I can't say that yet. We can't make it happen yet. Let me go in here. Like that. That's what it would look like. Okay. Now, most folks who are familiar with multi-level models, including pre-2018 Lisa, would be like, this is fine. There's nothing wrong with this. It's not fine, though. Why is it not fine, folks? I have a random slope that says the effect of being poor at the student level varies across schools. That's my intent. But is that actually what's here? It's not.
That's
So-
kind of a weird mixture where you're saying, I have a fixed slope, plus I'm randomizing within my fix, and that's just kind of weird. Wait, now, could you though, couldn't you just eliminate your gamma 1, 0 and then leave your U1C for your random slope?
We're going to do something analogous to that, but it's
Fair enough.
yeah, we're going to add another variable to the problem. So here's the issue. Without this fixed effect, we agreed that this fixed slope is smushed, right? And so we put in this main effect to unsmush this main effect. I'm saying that because interaction terms are forthcoming, of course. We would ideally like to do the same thing to unsmush this random slope. But there's no easy way to add the analog of the cluster mean as a random slope. So it is theoretically, mathematically possible, even though it makes zero sense, you can have a random slope of a level 2 variable across level 2 units. It's actually a trick that introduces heterogeneity of variance of the intercepts. But this is the topic of Vladimir's thesis. How well does it go when you try to estimate a random slope of a level 2 predictor at level 2?
Not good.
Not good. So convergence rates around what, 30, 40% in some cases?
Yes.
Mm-hmm.
It can vary between 34, 35 or 40% to 50%, depending on sample size. But you will always be at 50% if you have enough data.
Yeah, like so his most optimal conditions,
Exactly.
it was never above 50%. So like practically speaking, I don't think that's a solution that I can recommend. Like it's not going to work, and half the software programs are like, what? No, when you try to ask it for that.
And even if that works, what can you say about that random slope?
Exactly. Like it doesn't make any sense. It's like a math thing that's possible. But anyway, so we're going to fix it. But we're going to fix it in a way that preserves the within contextual version of the fixed effects. Because in clustered data, that is more common, because I think it's more useful in a lot of cases to talk about what is the incremental contribution of the group above and beyond the contribution of the individual. We want to keep the fixed effects phrased that way, but we want to unsmush this random slope. Ergo, we get to this crazy looking thing. So I have left beta 1, and I have left the fixed slope for it. So this fixed slope is going to be within, this one is going to be contextual, just as it was before. Rather than add the random slope to the original uncentered level 1 predictor, I am adding in a cluster mean centered version, but I'm not giving it a fixed effect. I'm only giving it a random effect. So it works out the same as you would expect. It's essentially, this is the within fixed effect and this is the within random effect. But it's accomplished via this sort of convoluted model so that I can keep the within contextual parameterization with respect to level 2. So in the code, I have the original version of the level 1 predictor as a fixed effect, and then I have the within cluster mean centered version as the random effect. So it is 2 different variables, 1 effect for each. And the same is true in R. We'll get to that down here, where we have the original one in the formula for the fixed effects and the cluster mean centered one inside the parentheses for the random effects. Normally, you would never want to estimate a random slope without the fixed slope that goes with it. This is an exception because it is already in the model, just attached to a different variable.
Okay, that's what my brain was going.
Yeah, like
How?
it's in there is the how, but normally you
No,
would
no,
not
no,
want to do that.
How, not how.
Mhm.
How.
Ow?
O-W, how.
Fair enough.
Brain was hurting.
Yes, indeed. In Stata, but not in R, also you have to add that you want a covariance among the random effects that pertain to the same dimension of sampling. Otherwise, that is not included. So if you're working on your next homework and you're not getting the log likelihood right when you get to that point, make sure you check this little thing right here. So in terms of the output, since this is the first random slope model I think we've seen this semester, I have it in both packages. First thing I want to mention, the level 1 slope has changed. It used to be -9 something and now it's -8. That's a weighting thing. This is now the average slope of the school slopes rather than a slope ignoring school just on one column of stacked data. So you can think of this as the center of a distribution. So in the average school, the difference between kids who pay for lunch or get a discount is -8. That's the center. The variance of that random slope for the cluster mean centered version of the predictor is 14. That's a big number. It looks like it's different than 0 if I just eyeball the confidence interval. What about this hypothesis test right there? Does that tell me if my random slope is needed? There's one important clue that answers the question. I'm going to zoom all the way in. There. This number right here. That's your clue. 3 degrees of freedom. It should be 2 if we're testing the random slope. So this test right here in Stata is testing the entirety of the random effects at the same time. So it's basically saying like, hey, can I just run a linear regression and be done with this? No. That's what it says. So this test is only useful sometimes, and this is not one of them. In Stata, though, you can do likelihood ratio tests. There's a command called estimate store, and you need a name for what you want to call it. I just named it after the model. SStat recovariance relevel school ID correlation is the command that turns your covariance in your random effects into a correlation. This is a -1. So remember paint from Tuesday with the slopes and the correlation? Should I get it back out? You're like, maybe. Very briefly. Mm-hmm.
I was thinking you were dealing with printing somehow.
No.
Our model, like, what?
So our slope is negative, right? This is a -8 slope to the best of my drawing ability here. And we have different slopes for different schools. I'm guessing that being poor is never good for you, so I'm not going to draw any positive lines here. So if we think about what a negative correlation means, the intercept is going to be the expected math score when this variable is 0. It's the within cluster version of this lunch variable. So it's at the average for the school. It's not actually for kids who pay for lunch or don't. It's in the middle. So if you are from a school that has relatively strong math at that point relative to other schools, a negative correlation means that you have a stronger effect of being poor, because higher intercepts go with lower slopes, like in terms of the distribution. A lower slope here is more negative. You got to get the paint out to make this work. Like, it's very tricky to keep that straight if you have without knowing the direction. So let's see here. Yep. So in Stata, I'm going to test the contribution of that random slope variance and the covariance with the intercept by comparing the models. So this one has the 2 degrees of freedom that it's supposed to have, which is reassuring. And the chi-square test statistic is 90. That means, yes, it is decidedly significant. And this note here is reminding us not to screw this up. The reported degrees of freedom assumes the null hypothesis is not on the boundary of the parameter space. This is the mixture thing. I think I've mentioned it once or twice. Technically speaking, because the random slope variance can't go negative, the comparison should not use 2 degrees of freedom. It should use a mixture of 2 with 1 degree of freedom for when it wanted to go negative but couldn't, essentially. It's on the boundary. So if you use a proper mixture chi-square, your critical value for a 2 degree of freedom change is 5.14. If you're like, I don't want to think about this, I'm going to ignore this problem, the critical value is 5.99. So very few cases where this is going to matter. I just don't care. I'm okay with being a little bit conservative, but for anything that's on the bubble, you would want to pay attention to this. And then what you were asking about earlier before class, note, LR tests based on REML are valid only when the fixed effect specification is identical across models. So that's one of the model comparison rules that we learned early on. That's why all of my examples add the fixed effects in one step and then add the random effects in a second step so that I keep the fixed part the same so that I can do the likelihood ratio test. I do that because we're in REML, but I also do that because, to me, it doesn't make sense to add fixed and random at the same time, because the change in fit could reflect just the fixed part, just the random part, or both, and I would want to know about both of them. So I do it in layers for that reason as well. So there's the correlation directly given in R instead of covariance. RENOVA is how we do likelihood ratio tests. There's my 2 degrees of freedom. I'm going to compute a couple of things regarding my random slope. One is a confidence interval. So the middle of the confidence interval is the fixed effect, the -8. That's the average poverty gap, plus or minus 1.96 to create a 95% interval, times the square root of 14. That was the variance. So what I'm doing is fixed effect in the middle, plus or minus 2 standard deviations around it to describe the expected variability of the slope in the schools in my sample.
3.77, basically, that value. I could be wrong, but I thought.
Which one?
If you go straight up directly across from the 14, isn't that the 3.77?
Oh. Yes, it is.
Okay.
None of the other packages I use in my life print standard deviation, so I'm not even used to finding them.
I'm just
But yes.
inquiring if that's,
Yep, no, it's there.
okay.
Yep, same thing. Yep. So that interval works out to be -15 to -1. So yes, it is never good to be poor. All the slopes are negative, or at least the majority of them would be. So this is a little more concrete. Like if I'm talking to a school administrator, I can say, hey, some of the schools in this Midwestern rectangular state have gaps that are 15 points, and some only have gaps that are 1. Why is that? what kind of predictors would we need to explain? Whether it's a 15 gap school or a 1 gap school. School level things, right? Because this is a school characteristic now. It is another school level outcome. It's no longer just mean math. It's mean math and gap math. Math gap? Math gap. I like that. The math gap. Slope reliability. I am computing that here, and it works out to be 0.58, so not great for this, but it's a binary predictor. Like, there's not a lot of information in it in the first place. To be able to do these things then in software, in Stata, I saved and then printed the model output, found the values that I wanted, saved the results of the variances for further comparison and effect size, and then used those saved results to compute these characteristics. In R, I did the same thing with the as data frame for the var core, extracting this, turning it into a table I can work with, and then plugged in the places for the information that I want. So this column is variances and covariances. So like this one right here is the covariance. This column is either standard deviations or correlations. So it's all in one nice compact table. Now I told you I only have one predictor in my data set, right? That's not going to stop me. We're going to answer the question of why is it that being poor sucks more in some schools than others? Maybe it depends on how many poor kids are at your school. That's a reasonable thing. Now that simple idea, right? Does the effect of being poor depend on how many poor kids are at your school? Hang on to that, because this gets very complicated. But that's the core idea of what we're trying to examine. So we are introducing a cross-level interaction with the original binary predictor. So then we can say, is that slope moderated by the school's proportion of kids who get discounted lunch? If so, then that random slope variance, it's not tied to the same predictor, but it's conceptually the same thing, should go down. So we add in this here with the interaction term.
Sorry, you said that
Yep.
U2C should go down.
It should. In the same line, sort of. Like I wrote the equation so that my rule stays the same. There's just a semicolon in between. But yes, this is what should go down. Yep. However, I want this to reflect moderation of the within effect. Does it?
Don't you need an interaction?
I need another interaction. Yeah, this is a smushed interaction. So in the same way that we started with this, and it didn't get unsmushed until we added in the cluster mean main effect, we're starting with this cross-level interaction, and it needs to get unsmushed by building the interaction at level 2 as well. And that's where we get into the quadratic, because this is my moderator times itself. So if we just add the first cross-level interaction, it is not significant, according to that, but it looks like it's an opposite direction, so it would be weakening the effect. So in this case, for every, move it over, for every 10% more poor kids in your school, this slope becomes less negative by 0.4. So it's a dampening type of thing. And you could go the other way in terms of interpreting it. However, which variance component should have been explained by this, did we say? Random slope, right? We did. But the intercept variance actually went down. Excuse me, R square went down, intercept variance went up. That's what that means. It went the wrong way. This is an example of a misspecification. So we actually added intercept variance because right now the model is saying that the extent of moderation is the same within as it is between. So we're going to unsmush it by adding in between level moderation that is separate, and that is this term out here. So in the same way that this is the within main effect and this is the contextual main effect, this is now the within interaction and this is the contextual interaction. Guiding principle, if you're not using cluster mean centering at level 1, whatever you do at level 1, you got to do at level 2.
If you are doing cluster mean centering.
If you are doing cluster mean centering at level 1, you do not. Because then you're not saying that the level 2 term is equal to the level 1 term. By leaving it out, you're saying the level 2 term is not there. Yep. Let me. Yeah, I had to have a lot of caffeine this morning to make this work, by the way. Just so you know,
So
right?
Are you on 7-Up now?
I am. Sprite Zero
Sprite.
this week,
Yeah,
actually.
same difference.
It was on sale, so you'll see like whatever Hy-Vee had on sale last week. Come to school with me. No, we did this like, I don't know, in September, sometime around then. So if we're using cluster mean centering at level 1, we still put in the cluster mean at level 2, usually. These would be the two variables we'd consider. And the beauty of cluster mean centering is that each predictor, its slope means what you think it means, regardless of whether the other one's in the model. So if I only put in the level 1 slope, I allow for a within main effect, and I say that the between main effect is 0. If I only put in the cluster mean, I'm allowing the between effect to exist, but then I'm saying the within effect is 0. And if I put them both in, not only do they retain their interpretations, but if you did your centering correctly, they will be the exact same numbers because each is staying in its level, in its lane. So I usually recommend that folks set things up this way because it's easier to not screw it up. And if you want to talk about contextual effects, you can ask for them as linear combinations after the fact. But down here, under constant centering, so in our current example, the fact that it's a binary predictor means we centered at 0, right? Like it's still constant centered, it's just being left alone. Well, if I only put in that original predictor, then at level 1, I have a smushed effect. And the problem with the smushed effect is that they're both assumed to be equal, not 0, but equal. So then when you put them both in, they change into this interpretation instead. So the same thing is going to be true with any predictor that interacts with this level 1 variable. It's a smushed interaction until you put in the analog to it at level 2. Whatever you do at level 1, you got to do at level 2 if you're not cluster mean centering. If you are cluster mean centering, you can put in whatever you want, but leaving out level 2 is weird a lot of the time. Let's say that you have cluster mean centered whatever. You're saying that for every unit more of this I have than the rest of my school. That's what that means. But level 2, what the rest of the school is relative to, is missing from the model. That's weird. Like you're saying only relative variation matters and not absolute. There's not many constructs for which that would be true. At least not in cluster data. In longitudinal, I can think of a few things like that. But that's a different class. All right, did that help? Okay. Okay. Where are we at? I know. I'm like, oh, I'm rethinking this decision to leave the Mountain Dew at home right now.
You're going upstairs.
They don't sell Mountain Dew on this freaking campus. It's only Coke. It's a Pepsi product. No, at KU, when I was a grad student, they had both for a while, but then they switched to this model where like the university, like Coke is sponsoring them, and they promised to only sell Coke on the campus. So in the grad student offices, we had a bootleg Pepsi business running. We would take turns, like each of us once a month would go to the grocery store and just buy a crap ton of soda, and we'd sell it to ourselves for like 50 cents a can. And it was like only the Pepsi that we liked in the office. So fight the man. I don't want Coke. I want Mountain Dew, damn it. Diet Mountain Dew in particular. Yes.
So could you have done this study with cluster mean centers instead of this route?
Yes. Probably should have, in hindsight.
Well, no.
But-
I'm not saying that, coulda or shoulda, but I'm just saying, I just want you could have.
Mhm.
Okay.
So at this point, both the main effects and the interactions are unsmushed. And we have model implied between effects. So the simple slope, as it's known, the conditional slope, is found by adding the within main effect and the contextual main effect. The between level interaction, rather than the contextual interaction, is formed with the level 1 cross-level interaction term plus the new quadratic one that's contextual. So it's the same concept, just at a higher level of complexity. Now, what the heck does it mean? That's the trickier part. So lots of code here for Stata folks. This is computing pseudo R-squares and changes in pseudo R-squares relative to the previous model. Total R-squares as well. In R, to square things, you have this function, inhibitor, right? Yes, that way it doesn't like literally square it, it's just telling you to put this variable in here as that term. All right. I'm not even gonna ask who's feeling brave. At this point, I'm not even feeling brave, but I'm gonna try
What are
this.
you attempting to do?
I'm gonna walk through the interpretation of these bad boys. That's what I'm attempting to do.
Give it a shot.
Yep, I'm gonna give it a shot. So, where's 0? Right, that's the first thing I gotta think about.
30%?
Yeah, so 0 is a kid who pays for lunch, okay, according to this, who goes to a school where 30% of the kids get a discount. And that's it, right? Because the rest of these are combinations of those two. So that's my reference person. Now, each of these is conditional because it's part of interaction terms. So this is the math gap, specifically when interacting predictors are 0, which is this one. So that translates into the math gap at schools where 30% of the kids get a discount. Now we go with the signs. According to this interaction, as you get more poor kids in your school, as the cluster mean goes up, what happens to that math gap? Does it get bigger or smaller? Smaller because it's negative, exactly. Smaller because the signs are opposite. So this is a less negative. It is less bad to be poor if you go to a school with more poor kids. And I'm gonna do my trick here. For every 10% more poor kids, the gap here becomes smaller by 0.5. Interaction terms moderate slopes. Slopes then move predicted outcomes. So the correct way to talk about an interaction is what is it doing to the slopes? So I will say that again. For every 10% more poor kids as the moderator, this slope, this gap, is smaller by 0.5. Okay, how are we doing? I could do it the other way. I could talk about how the school effect is different in poor kids and not poor kids, but that feels a little less like intuitive, so I'm not going to do that one. Now this one. Quadratics. Signs are the same. What's that tell us? Yeah, more downer. This is a negative slope that becomes more negative as you move up the variable. So the variable in question is cluster mean lunch composition. This obeys the same rules in terms of it being a simple slope that is conditional on any moderating predictors being 0. So this is the effect of cluster mean lunch specifically at the 0.3 point on this curve. The slope of the line that is tangent to the curve at 0.3. That's what negative 18 is. Yes?
Is that only condition on the quadratic interaction or is also condition on the
Yep. So this is also conditional on this one, exactly. So we are saying that this is specifically for kids who pay for lunch also. But if I work on this one, what do I have to do to the quadratic to talk about how it changes the linear slope of this variable?
forget if it's twice or half.
That's it. That's where I'm going. Every class I teach, I'm going to talk about this in. Every one. So the quadratic slope is half the rate of acceleration or deceleration. So we're talking about finding the first derivative of a function and the second derivative. And when you take the first one, the 2 that's in the squared comes down in front. It's twice. So what this means is that that negative slope of minus 18 becomes more negative by 22 per unit of this moderator. But the units are weird in this moderator as we're talking. But the pattern still holds. It's the difference between schools as a function of their lunch composition increases as you get more poor kids in them. Then the between interaction, if I wanted to find that, would be these two things added together. And I think I did that down here. Yep, probably. Yep. Question?
Yeah, Lisa. Can you go back to the coefficients, please?
I can.
That one works. Any of both. So in this case, the third coefficient, the minus 18, for the cluster mean of our for the cluster mean of the level 1, we know that 18 right now is the instantaneous rate of change for the schools, right? Although we know that based on, given the cross-level interaction, that's conditioned on students at level 1 being 0, which is students who pay, right? Although given that we have a quadratic term, that specific coefficient is conditioned on itself being 0, which is for the schools at 13%.
Right. Yes.
So I'm trying to understand this because right now we would say that that minus 18 should be capturing like the whole difference between a school fully composed of students who pay versus a composition of students.
Yes. 0 to 100.
Yes. However, it is fixed at 50 because it's fixed on itself. How can we capturing the whole range but be conditioned on one of the values at the same time?
It sounds crazy, but it's not a contradiction. I mean, these are the units of the variable. A unit is the entire range of the variable. We're estimating a slope per unit, like at one particular point on the curve, because it's going to change, right? It's this kind of function. So you can't just say there's one slope. It's like, are you up here? Are you down here? Are you all the way down here?
Okay, that makes sense. Okay.
I have pictures. Since it's 142, let me just show you a picture, and then we'll pick this up after the formative assessment next time. I don't want to rush things on. Where's my pictures? Words. Okay. That one? Yeah, this one. This is the one I want. It's a very small effect. But if you look at the spread of these lovely colorful lines, the gap between red and green is smaller than the gap between green and blue and green and purple. So there's more school differences as you move up the variable. School matters more. It's a nonlinear effect. It gets stronger at higher levels. And that is being shown as the contextual effect in this, as the vertical distance between these. So I don't know if that helps at all, but This is a whole thing, by the way. This took me forever last time, so we're going to have to spend some time on it just so I don't feel bad. Trying to figure out how to plot these things with representative values is surprisingly challenging. So I do want to walk through like some of that because a lot of you are going to have to figure this out for yourselves.
Sharpie.
Sharpie. And it's important to show predictions that could actually happen. Right? Like you can't, like theoretically, I could have a school with 0% poor kids, right? But then I can't show the effect of being poor. Like there's no poor kids. You can't see it. So you don't want to wander into those sorts of territories where you're plotting impossible combinations. It's a little tricky, but all right. 144, it's Thursday. That means I say have a good weekend. Yes, work on your formative assessment. Let me know if you need anything with respect to your projects or otherwise. Have good weekends. Yay. Thanks for being here. See you on the other side. Happy Halloween. Sure.